Thank you very much. Our final speaker this afternoon is Professor Juan Maldacena from the Institute for Advanced Study in Princeton. Professor Maldacena discovered something called gauge gravity duality, or the ADS-CFT correspondence, which really revolutionized our understanding of string theory. It has dominated work in this field for approximately the past 20 years. Professor Maldacena is a member of the World Academy of Science as well as the United States National Academy of Science. And he's going to talk today about quantum mechanics and space-time.
Oh, thank you. Thank you very much. Thank you. So it's a great honor and pleasure to be here in yeah, I'm it's a great pleasure to be here, and I hope, let's see, okay, very good. So I'll be talking about quantum mechanics and the geometry of space-time. So we've heard many times that general relativity produced two stunning predictions. The first one is black holes, and the second is the expanding universe. And these predictions were so surprising that Einstein himself was surprised by them and refused to believe them in some ways. So I love this phrase that Einstein is supposed to have told Lemaitre. He said, "Your math is great, but your physics is dismal," when Lemaitre was trying to explain the expanding universe to Einstein. And I love it because that's often what physicists tell string theorists. No? Now, in both cases, these predictions are surprising because a drastic stretching of space and time, or time, are involved. Now, if we want to incorporate quantum mechanics into general relativity, there is a very simple approach, which is to say you have general relativity. General relativity is a classical field theory. And then we ought to quantize this theory. Now, it is hard to change the shape of space-time. So here the whole Earth is barely changing the shape of space-time around it. And so for most situations, we can think of quantum fields in a fixed geometry, and that's usually a good approximation. And we can consider even gravitons on that fixed geometry. And this leads essentially to thinking about the quantum version of general relativity as an effective field theory. And this is a good systematic low energy approximation. And it's good for low energy questions, but it's not valid for all questions. I mean, it certainly fails for the beginning of the Big Bang, for example, or the interior of the black holes. But it can answer some, this simple approach can give also surprising predictions. And there are two surprising predictions of this approach. And the first one is that black holes have a temperature. So the temperature is proportional to 1 over the size of the black hole. So if we start with some big black hole and we make it smaller, and it could look red, and if we make it even smaller, it could look white. So we can really have white black holes. So so in this sense, they are surprising. Even the name is wrong. Okay. So if you have a black hole whose size is of the order of the wavelength of light, you would see it white. Now, the second surprising prediction, closely connected to the previous one, is that an accelerating universe also has a temperature. So the formula is very similar. So the temperature is proportional to 1 over the size of the apparent horizon in this universe. And both effects are proportional to h bar, so they are quantum mechanical effects. And this, and they basically have the same origin, as we'll see in a moment. And this second effect, so the first effect is predicted theoretically, but hasn't been observed experimentally, because the black holes that are produced in nature are very big and have very tiny temperatures, which are not experimentally detectable. However, the second effect, as we'll see, is very relevant for us. And what makes it relevant is the theory of inflation. So this is the idea that there is a period of almost constant acceleration in the very early universe, where the universe is expanding with constant acceleration. And in the classical theory, this produces a very large and homogeneous universe. So if we had just classical general relativity coupled to the scalar field that produces inflation, we would produce a perfectly homogeneous universe. However, quantum fluctuations lead to give rise to those to the temperature, or the temperature, which is the same effect, give rise to small fluctuations, and these small fluctuations are the fluctuations we see in the CMB and are the fluctuations that are the seeds for cosmic structures like galaxies and so on. So we see that quantum mechanics seems to be crucial for understanding the large-scale geometry of the universe, and certainly the theory of inflation, including these quantum effects, is the best theory we have today to describe this large-scale structure. So we often think that quantum mechanics is important for understanding the geometry at very small distances, but even if we ask the question of why the geometry of the universe at long distances is what it is, we see that we come back to understanding the interaction between quantum mechanics and geometry. Okay. Now, since this effect of the temperature, the Hawking temperature, or the temperature in de Sitter space, is so important, I thought that I would just give a short description of how it arises. So it's useful to consider first another problem, slightly different problem. So we consider just Minkowski space, or just simply flat space, and we try to look at flat space from the perspective of an accelerating observer. So imagine you are an observer following a trajectory with constant acceleration, right? So we are there with a rocket, let's say, moving with constant acceleration. And this constant acceleration measures some time, and the operator that generates these time translations is the boost. So in order to go from this point here on the trajectory to a later point on the trajectory, that simply corresponds to a boost around the origin. So a Lorentz transformation around the origin. And if we take this time translation generator and we continue it to Euclidean time, as we often do in order to think about the preparation of the quantum state and so on, then we find that the boost becomes a rotation. So if we take the same picture and we make this time coordinate, the time as seen by the accelerated observer, we continue it to Euclidean time, then we see that that time translation corresponds to translation around the origin. But the interesting feature about this is that this rotation is periodic. So we start rotating around the origin and we come back to the same situation. And we know that if we take a quantum system and we consider it in Euclidean time with periodic Euclidean time, that's equivalent to considering the thermal ensemble, or we consider in a thermal state. And then we get the temperature, which is proportional to, well, the inverse temperature is proportional to 2 pi r, so the physical size of this circle. And this is an effect that was first discovered, well, it was found in these terms by Bisoniano and Wichmann, but Unruh really realized independently that it meant that an observer who's accelerating would actually see this temperature or measure this temperature if he had a thermometer. So that's a physical effect. And this effect has one surprising aspect, which is that we started in quantum mechanics on a state that was just a unique state, the vacuum, but the accelerating observer sees this state as a mixed state, so as a thermal state. And this arises because the accelerating observer has access only to the right wedge, so he can only receive signals from this, well, he cannot certainly not receive signals from this side of the space-time, and so there are parts of the space-time that he cannot see. And the fact that he sees the temperature is related to the fact that the vacuum is a very highly entangled state. So if you start with the vacuum state, so that's a pure state, but if there are some degrees of freedom, some quantum degrees of freedom that you cannot see, and you only see parts of the degrees of freedom, then if you have an entangled state, then that part of the degrees of freedom could look thermal, could look like a mixed state. Now, going back to the black hole case, so we can imagine a black hole that forms from collapse, for example, We often, in order to describe black holes and their associated geometry, we use these diagrams, which are called Penrose-Carter diagrams, and they basically represent their little map of the space-time geometry. The vertical direction corresponds to the time direction, and the horizontal direction is the radial direction, for example, and then we have some spheres that I'm not drawing explicitly. And here in these diagrams, the metric of spacetime has been rescaled, but we preserve the fact that light rays move at 45 degrees, so any time-like trajectory will be a line moving vertically at not more than 45 degrees. So when we have a black hole, there are some regions of the spacetime that cannot send signals to the outside. So for example, if we have an event here in the interior, it can send signals, but those signals will end up at the singularity and will not make it to the outside. So if we stay outside the horizon, so let's say we are an observer who stays outside the horizon at a fixed distance from the horizon, we'll have to accelerate in order not to fall into the black hole, more or less very much the same way that we're accelerating here, but not to fall into the Earth. Then will be somewhat similar to that, the geometry near this region is very similar to the geometry we had in Minkowski space, and for that reason, this observer will see a temperature, and that's basically the physical origin of the Hawking temperature. Now, the fact that there is a temperature for black holes, which came from special relativity near the black hole horizon, together with quantum mechanics, plus the relationship, plus Einstein's equations, which imply a relationship between the size and the mass of the black hole. And then we can use the first law of thermodynamics to define an entropy. So this is just the equation we use to define the entropy. We can then calculate, by integrating this, we can calculate the entropy, and it turns out that it's given by a very simple formula, given by the area of the horizon divided by h bar g Newton. So here we see that as we send h bar to 0, we get a huge entropy. So the entropy is infinite in the classical limit. In addition, the entropy defined in this way obeys the area, it obeys a second law. So the area of the horizon increases. So this had been proven before by Hawking, before the temperature was discovered. And so we see that that fact that comes from classical Einstein's equations translates into Kazan interpretation as the increase of the entropy. So this gives an interesting relationship between Einstein's equations and thermodynamics. So we see that in some regimes, Einstein's equations have the same implications as thermodynamics and reduce to thermodynamics. So all these formulas suggest that if we view the black hole from outside, then general relativity is giving us a thermodynamic or approximate description of the system if we stay outside. Quantum mechanics suggests that there should be an exact description where the entropy, the fine-grained entropy, does not increase as seen from the outside, and where Hawking radiation is pure, so it's not mixed, that it would be mixed only if we make some approximation. Now, also, if we think about a black hole that forms and then it evaporates by emitting Hawking radiation, then we would start with a situation where we form a black hole and then we end up with radiation, and that looks similar to a scattering process where we send something in and something comes out, and the general rules of quantum mechanics implies that this transformation should be a unitary transformation and there should be no information loss. So that also suggests that there should be such a description. Now, I would suggest that the fact that general relativity implies that there is this second law suggests that information is not lost. I mean, if it were true that the interior of the black hole should be thought as a second asymptotic region, then there is no reason why the second law should hold if you stay outside the horizon. So certainly that would not be true if we just keep part of the system. So if we only consider this room and then some air comes out of this room, it can carry entropy, and the second law doesn't have to hold inside the room. But that's not the case when we remain outside black holes. So the second law continues to hold if we include this gravitational contribution to the entropy. So one wonders whether there is some way of describing this in a way that respects unitarity from the outside, and that one would need to identify the degrees of freedom that give rise to that black hole entropy. since the black hole entropy depends on gravity, so it's given just simply by this nice geometrical formula of Bekenstein and Hawking, then it implies that if we manage to identify these degrees of freedom, this will be the degrees of freedom of quantum gravity. And so they should reveal somehow something about the structure of space-time. And then in order to find the unitary description, we should also understand the dynamics of these degrees of freedom. Now, doing this is something that requires going beyond perturbation theory, certainly definitely beyond gravity as an effective field theory. And so for that purpose, we turn to string theory. And so string theory started out defined in terms of a perturbative expansion, as Ed explained. And that perturbative expansion doesn't have the ultraviolet problems that the perturbative expansion in quantum field theory has. And however, for the black hole problem, we really need to go beyond perturbation theory. And it turns out that string theory contains some interesting solitons, which are called d-branes. And these solitons, thinking about these solitons, led to inspired some non-perturbative definitions of the theories in some cases. So first it was through something called matrix theory, and then also the gauge-gravity duality. So I'll describe in more detail the second example, the gauge-gravity duality. So the gauge-gravity duality is a kind of bridge that relates two theories of physics. One is the kind of theories we are discussing, theories with a dynamical spacetime, a quantum mechanical spacetime, for example, string theory or quantum gravity theories. And on the other hand, we have a quantum field theory or theory of quantum interacting particles, so conventional quantum field theory. And the simplest examples consider gravity in an asymptotically anti-de Sitter space, so a space which has constant negative curvature. Anti-de Sitter space is essentially like hyperbolic space. So hyperbolic space is the simplest negatively curved space. It was the inspiration for developing non-Euclidean geometries, one of the first examples of non-Euclidean geometries. And we call anti-de Sitter the version of hyperbolic space that has one-time-like direction. And so in this duality, in this relationship, what happens is that in the interior of this space, we have quantum gravity. So we have the quantum mechanical version of hyperbolic space, or you can view it as the simplest example of quantum gravity, in the same way that hyperbolic space was the simplest example of curved space. And so here in the interior we have dynamical gravity, and on the boundary we have quantum field theory, a theory of quantum interacting particles. And this is a duality in the sense that we could either think of the theory defining through the interior or in terms of the boundary. And the boundary lives just purely, the boundary particles live purely on the boundary. And so then, from that point of view, the radial direction is an emergent direction, and the whole spacetime in the interior emerges from these dynamics in a way some features of which we'll discuss later. Now, the argument that these two things should be related was based on these d-branes that Polchinski had discovered. And these d-branes are some soliton objects that have some tension. That you could think of them as membranes stretched in space-time. And they carry some tension and some charges. And if you put a large collection of these branes, they will curve the space-time around, and you can calculate how they curve the space-time around using Einstein equations. And that leads to certain black brane geometries. So these are generalizations of black hole geometries. And the geometries you get are very similar to extremal black holes. Now, Polchinski had given a very precise description of how to think about these d-branes in string theory. And one could take the low energy limit of that description, and we get a certain supersymmetric version of quantum thermodynamics in 4 dimensions. This comes from the excitations on these branes. And the near horizon geometry of these black branes is a certain anti-de Sitter space, and since we started in 10 dimensions, we also have a 5 sphere. And so we get string theory in a very specific space. Now, here I've given the specific names of these theories very precisely, but there are relationships like this in many other cases. Now, this gives a relationship between large N gauge theories and strings. And this relationship has been anticipated by Toff, and is based on the idea that a gluon carries a color and an anti-color. And we could consider an alternative theory where instead of having 3 colors as we have in ordinary quantum chromodynamics, we have n colors. So more mathematically, the gauge group would be SUN instead of SU3. And then if we take the large N limit, we find that the effective interactions between a particle, so we could consider states where the colors of one gluon are entangled or are the same as the anticolor of the next. And in such states, the interaction between such correlated colors and anticolors is very strong, while the interaction between colors that are not related to each other is relatively weak. And in this way, by taking the large N limit, keeping the effective interaction between correlated gluons strong, then we form this chain, so the elementary excitations will be chains in this space of colors, and that should behave essentially like strings in some space. That was the argument. And so these closed strings are what in QCD we would call glue balls, objects made purely out of gluons. And the string coupling is proportional to 1 over the number of colors. I should mention that these ideas are based on an experimental observation, which is just that we find these strings, we find some kind of strings in chromodynamics, and the best evidence one very good evidence for these strings comes from looking at the spectrum of mesons in chromodynamics. And so we find this linear relationship between the mass square of the mesons and their spins. So these are some elementary hadronic particles, strongly interacting particles. And this linear relation can be explained very simply in terms of a rotating string model, where that rotating string model predicts indeed that there should be a relationship between the mass square of the particle and its spin by a proportionality constant, which is the tension of these strings. So I point this out just to note that these strings that are made of gluons are certainly observed in nature, and they are relativistic strings, very similar to the strings we think about in string theory. And we think that these strings should correspond, so the particular strings of chromodynamics should correspond to strings which are very similar to the elementary strings we have in fundamental string theory, except that living on a curved space, in a space that has 1 more dimension. And in the particular case of n equal to 4 super Young-Mills, which is a particular supersymmetric theory of quantum chromodynamics, then we can find precisely which strings those are, and they are basically the strings of 10-dimensional string theory. Now, as Witten explained, when we consider a space which is weakly curved, then weakly curved means that the radius of curvature is much bigger than the typical size of a string, of an oscillating string, the typical size of the graviton viewed as an oscillating string. Then string theory reduces to gravity. So when this is much bigger than 1, the string theory reduces to gravity. Now it turns out that in this type of dualities, the radius of curvature in units of the size of the string is proportional to the effective field theory coupling, so the coupling between these gluons that are color correlated. And so it's raised to some positive power. So if we want to have a radius of curvature much bigger than the size of the string, so that Einstein gravity is a good approximation, then we are talking about quantum field theories which are very strongly coupled. Okay? In addition, since the Newton constant related to the string coupling goes like 1 over n squared, we also need a large n, so large number of fields, and also strong coupling. So we need these 2 conditions in order to get Einstein gravity in the interior. Now, one interesting aspect of this relationship is the emergence of this extra bulk direction with its dynamical gravity in the interior. And one simple cartoon picture for how this extra dimension emerges is the following. So you can think of the boundary excitations as little blobs. So the field here on the boundary is typically a scale invariant theory. And so you can have blobs of different size. So in order to specify an excitation on the boundary theory, we not only have to give the position in space, but also the size of that excitation. And since the theory is scale invariant, those blobs can have different sizes, and the blobs with different sizes are related by a symmetry in the theory, so they should have intrinsically the same characteristics. And we realize this in the bulk by saying that the red blob here is some particle or some string here in the bulk, and the blue one is exactly the same one, but displaced along the extra dimension. So we get a picture where, okay, so this one is not working, so what should I do? Oh, it's not working here, sorry. Okay, given that I took the effort to do this, I wanted to work. So we have some objects here in the bulk, which can be doing their own thing, and they are represented by very strongly interacting particles here on the boundary. Here, this picture doesn't represent the fact properly that we need a large number of particles and very strong interactions. Similarly, we can describe black holes in the interior, which correspond to, again, a fluid of very strongly interacting particles. Here, the blue dots should completely fill the boundary in a very uniform way. I just ran out of patience drawing here. But this is, again, a cartoon picture of how we view the black hole from the boundary theory. So it's a thermal gas of particles or fluid of particles. Saying it's a gas of particles is not a good idea because it really doesn't reflect the fact that they're very strongly interacting. So it's a very strongly interacting fluid of particles on the boundary. And we can calculate the entropy as, well, in two ways. So one is the area of the horizon using the Hawking-Bekenstein formula. And also we can calculate it as the number of states of this fluid in the boundary theory. So the fluid in the boundary theory is a thermal state that has many different microstates. And by counting those microstates, we can reproduce, in cases where we can count them in the strongly coupled theory, we can reproduce the Hawking-Bekenstein formula. And here the picture is that an object falling into the black hole would be a perturbation of the boundary theory that eventually thermalizes with the rest of the fluid. Now, this relationship has also led to an interesting relationship to hydrodynamics. So we said that the field theory at finite temperature should correspond to a black brane in this curved anti-de Sitter space. So we can consider a field theory, let's say, in flat space, and the black hole is a black hole which has some extended directions, sometimes called the black brane. And we can consider long-distance ripples on this black brane, so small deviations from the just straight black brane. And these correspond to hydrodynamic modes of this fluid, just correspond to small deformations of this fluid. Since this fluid exists in a theory which is translation and boost invariant, we can give it a small velocity of the fluid in one region and a different velocity far away, and this creates a perturbation that eventually will dissipate and will form again a uniform fluid. And so what is dissipation in the boundary theory and thermalization corresponds to absorption of this wave. So there is this wave outside the horizon that falls into the black hole. And in this way we can calculate transport coefficients such as the viscosity using wave equations on this background. So a complicated problem in a strongly interacting quantum field theory, such as calculating these transport coefficients, translates into a simple problem of solving wave equations on this geometric background. And one can show, and these people have shown, that Einstein's equations in this limit reduce to the equations of hydrodynamics. First, relativistic hydrodynamics, but you can also take the non-relativistic limit and find that it really also reduces to Navier-Stokes equations when the velocity of the fluid is much less than 1. And this picture has been useful to discover for the discovery of the role of anomalies in hydrodynamics. It was found that when one tried to compare the Einstein equations to the equations you get in hydrodynamics, they didn't match. So there wasn't a match. And it wasn't a match because the equations of hydrodynamics were not the correct ones when we have anomalies, global anomalies in the boundary theory. And then after understanding what goes on in these examples that have gravity duals, then this anomalous hydrodynamics could be understood in complete generality, even in cases which did not have a gravity dual. So this is an application of using Einstein gravity or Einstein's equations to learn something about a different field of physics, let's say the field of physics of hydrodynamics. So using this, you can form a black hole and predict what comes out using the boundary theory. So if you assume the duality, you get unitary evolution from the outside observer and no information lost. Now I said here, if you assume the duality, so one can ask how well established is this gauge gravity duality. So there is a lot of evidence in the simplest examples and also a lot of complicated examples and further evidence. And in the simplest examples, for large n, one can use the techniques of integrability, and one can do computations at any value of the effective coupling. And one can see how these chains of gluons, which are a very intuitive description of weak coupling, get transformed into the strings moving in 10 dimensions. This has been shown in a large series of papers by many authors. But we still don't have explicit change of variables between the bulk description and the boundary description. So I think a complete understanding of this relationship would be to find an explicit change of variables between the description in the boundary theory and the description in the interior. Much in the same way that we have let's say, a Fourier transform that allows us to change the description of a wave function from position space to momentum space, for example. So we are not there yet. However, in the meantime, one can use these dualities and one can turn black holes into a source of information. So, this works because strongly coupled field theory problems translate into simple gravity problems, as we have seen for the case of hydrodynamics before. And this has been used for heavy ion collision, for modeling heavy ion collisions, for trying to understand high temperature superconductors, etc. And has led to an application of geometry or the techniques of geometry and general relativity to other connections to other areas of physics. So rather than describing these applications in more detail, one could ask the question of why should strong coupling simplify the problem? Is there any other example in physics where having a strongly coupled system actually leads to a simplification? So an example is, imagine you had a gas of particles, and you want to describe the dynamics of this gas of particles in terms of hydrodynamics. In order for that to be successful, you need strong enough interactions to locally thermalize this gas. So if you had zero interactions or very weak interactions, then you would need to use the Boltzmann equation, which is more complicated than hydrodynamics. Now, what we think is going on in gravity is something vaguely similar. So the idea is that gravity should somehow be the hydrodynamics of entanglement. Now, I have no idea what this means. Maybe someone here has a better idea. But this is a theme that is currently being explored and which seems to have some ring of truth to it. Now, in the next few transparencies, I'll try to explain why I'm saying this. So these are more completely understood things. So the first point is the following. So the boundary theory is a local quantum field theory. Local means that really at the very heart of this theory you have local qubits that are defined locally at each point in space. You have some set of qubits. And in local quantum field theory, the vacuum is, as we've seen through the Hawking radiation, or even the case of Ringler, the radiation for an accelerated observer, is a highly entangled state. And so if we have all the qubits in the boundary theory, so here I've drawn just a few of these qubits. So they're all in some quantum state, highly correlated between the different ones. And this motion is just trying to represent the fact that if we restrict attention to, let's say, the blue region, then we'll see these qubits as being in a mixed state. So they will not be in a pure quantum state, but they will be in a mixed state. And one can calculate, one can quantify the degree of mixture, or how many different microstates we have, by calculating the entropy, so associated to the density matrix with which we would describe that mixed state. So that roughly speaking is the amount of this entropy, is the amount of disorder that we would see in this set of qubits if we only restricted the attention to these qubits, starting with the vacuum state. And we could do this not only for the vacuum, but for any state. And in theories that have a gravity dual, that entropy can be computed in a simple way by calculating the area of a minimal surface, which ends on the boundaries of this region at the boundary. So this is a formula which is very similar to the Hawking-Bekenstein formula. And it's in some sense a generalization of the Hawking-Bekenstein formula for situations where we don't have a Killing vector. So we see this connection between entanglement and geometry. So the entanglement pattern in the state of the boundary theory can translate into geometrical features in the interior. So what I described in the previous transparency was the particular case of the vacuum, where we have the perfect hyperbolic space in the interior, and this is just one of the hyperbolic space geodesic surfaces. But if we were to change the vacuum to some other state, that would be a state with a different geometry in the interior, then the shape of this curve would change, and the amount of entanglement would depend on the geometric features of that state in the interior. So we see that spacetime is closely connected to the entanglement properties of the fundamental degrees of freedom. And so there's a slogan, which I also don't understand, which is somehow that the entanglement is the glue that holds spacetime together. And just to illustrate this, I'll try to describe perhaps the most extreme version of this. And this will take us first to a description of a certain spacetime, which is the two-sided Schwarzschild solution. So this spacetime is essentially the spacetime that Schwarzschild found just months after the discovery of general relativity, except that he found it in coordinates which he wrote some coordinates which are good outside in this region. So this region represents, so here far away we have flat space, flat Minkowski space, and this surface here are the horizons of the black hole. So r equal to 0 in the Schwarzschild. Well, r equal to the r. Well, this is the place in the Schwarzschild solution where the time component of the metric was shrinking to 0 in the original Schwarzschild coordinates. It was later understood that you can continue that metric towards the interior. Eddington, I guess, was the first one to write the coordinate system, though he apparently didn't realize he was describing the interior. Lemaitre was the first one to say that you could go to the horizon. Einstein and Rosen realized that if you take just this surface, you can continue this surface and through the horizon and into a second side where you have a second asymptotic region, a second asymptotically flat space region. And then eventually Kruskal gave us this full picture of extending that original solution in the maximal possible way so that we get this solution. So we have vacuum everywhere. That's the simplest spherical symmetric solution of Einstein gravity. So we have Einstein gravity is our theory of general relativity, and this is the simplest spherically symmetric solution. If we have a black hole that forms from matter, as we saw in the Penrose diagrams we had before, we only get the right part of this region, so only a portion of this diagram. However, we can still ask, what is the interpretation of this solution? What's the interpretation of this simplest solution we have in Einstein gravity? Now, that simplest solution in asymptotically flat space has a complete analog in anti-de Sitter space, so in these curved spaces that we were discussing. So again, it's a black hole, so which this part of the solution corresponds to a black hole in anti-de Sitter space, similar to that picture that we saw before of the anti-de Sitter space with a black object in the center. And this again has a second side and a second boundary, a second asymptotic region. And in this case, we can make a little more precise statement of what the how we should describe this. So recall that before we said that the black hole is a thermal state from the point of view of the boundary theory. That's a black hole seen from the outside, and that looks like a thermal state here. But the idea is that if we have this full geometry, now we have two boundaries. We have the left boundary and the right boundary, so we have two separate field theories, two separate non-interacting field theories. And the idea is that this geometry should correspond to an entangled state in these two field theories. So we have a set of states on the right theory and a set of states in the left theory, and we form this particular entangled state, which is called the thermal field double. It was considered for different reasons when thinking about thermal field theories. And this then, it should be the state. This is a pure state in the Hilbert space, which is a product of the Hilbert spaces of the two field theories. And that should describe this geometry. So that's there is, I think, a good argument that this should be the case, but it's disputed by some workers of the field. So here we see that we have a geometric connection between the left and right hand side that doesn't arise from a dynamical connection of the fundamental degrees of freedom, but is arising purely because of the entanglement. So here, similarly, the Schwarzschild solution should be viewed as entangled, some kind of entangled black hole between two different spacetimes. This is a little hard to think about. So instead of thinking about that, we think about the closely related situation where we have two black holes, but now living in the same spacetime. Where we have two black holes and they're identified to the interior. So these are two black holes that are sharing an interior. Now, if we have two black holes in nature, they will not be described by this geometry because we only have one exterior, but this is a geometry which we could consider. And this geometry looks like a wormhole. So if you can have these two black holes very far from each other, one in this galaxy, the other in another galaxy. If you are 1 meter outside this black hole, and your friend is 1 meter outside the other black hole, the distance in the outside could be millions of light years. But the distance through the inside, the spatial distance, could be just 2 meters. Okay? Now, if you try to enter the horizon and go and visit your friend, then you would start out from the outside, and you would try to visit your friend, but you find that this horizon starts moving away from you, and you will end up at the singularity, and you will not be able to go to the other side, which is a good thing. So these solutions, which are natural solutions to general relativity, do not lead to a violation of the principle of general relativity, which is that no signals can propagate faster than light somehow in the ambient space. Otherwise, we'll have some confusing situation. So the equations of relativity themselves do not allow us to construct traversable wormholes, which I think is an important physical principle. So these are not the wormholes of science fiction. Now these wormholes, however, can be arranged to produce a forbidden meeting. So imagine there are two people whose families want to keep apart. And they are sent to different galaxies in the far future. But they somehow manage to arrange to produce a pair of black holes in this particular entangled state. So what they can do is, if these two black holes share an interior, they can both jump into their respective black holes and actually meet in the inside. The people from the outside will just see them committing suicide, just dropping into their respective black holes and dying. But they actually met inside, but they cannot tell anyone outside. So this suggests a correspondence between these Einstein-Rosen bridges or wormholes and entangled states. And certainly in this particular case of the wormhole, we want to interpret them as an EPR pair of two black holes in a very particular entangled state. So we see that large amounts of entanglement in this particular case can give rise to a geometric connection, but we think that this might be a more generic property of quantum gravity, and which one can call this ER equal to EPR correspondence, relating two papers that Einstein and Rosen wrote, one with Podolsky, but they wrote actually these two papers in the same year. And one can complicate the entanglement pattern of the two-sided black hole and get a slightly longer wormhole. This has been studied by several people. Now, the black hole interior is not completely understood in the sense that we don't understand how to describe the black hole interior from the point of view of the boundary theory, even whether we can do this. So general relativity certainly tells us that black holes should have an interior, but general relativity doesn't tell us why the exterior theory is unitary. On the other hand, these boundary descriptions tell us why the exterior theory is unitary, but they don't tell us whether there is actually an interior. And there are some paradoxes that arise in some naive constructions, as have been pointed out by Mathur and Almeri, Marol, Kroshinsky, and Solik. And this is really an active area. It's been explored, and there are many ideas for what to do with it. So there are many ideas that people have suggested, and maybe some of them are wrong. Maybe the correct picture is to combine all of these ideas in a coherent fashion. So we've seen that quantum mechanics in curved spacetime gave rise to interesting effects, Hawking radiation and the emergence of primordial inflationary fluctuations. These effects are crucial for explaining features of our universe. And black hole thermodynamics poses very interesting problems. Understanding the entropy, the unitarity as seen from the outside, understanding the information problem, understanding the interior, etc. And we hope that exploration of these problems will lead to, exploration of this problem has led to connections between strongly coupled quantum field theories and gravity, and it also has led to practical applications of general relativity to other fields of physics. So people who are interested in superconductors, for example, sometimes write down Einstein's equations to analyze toy models and so on. We've seen that patterns of entanglement seem to be closely connected to geometry, and there's been a lot of work in this direction, which I haven't been able to review, but it's one of the very actively explored areas. And I should say that the black hole interior continues to be a puzzling problem, whose resolution will probably give us new insights into the structure of space-time. And not only that, but probably understanding fully this problem will also lead to understanding of cosmology, because after all, the interior of a black hole looks like a collapsing cosmology. So probably understanding it properly will also lead to understanding cosmology. And well, thank you very much.
Thank you very much. Well, that concludes this special session. I want to thank all the speakers for their excellent talks. And I especially want to thank Svante Wadia and the other organizers for arranging this wonderful celebration of the Einstein Centennial.